Picture this. It is 2023. You're an engineer on a high-stakes machine learning team at a healthcare AI company.
Oh, a very relatable scenario.
Right. And your task seems, well, incredibly straightforward. You just need to run inference on 500 pathology slide images overnight.
Which, sounds simple enough.
Yeah, I mean, you've got a beast of a server, like 64 gigabytes of RAM. Each image is maybe 1 to 2 gigabytes.
So the math works out. Technically, the dataset fits just fine.
Exactly. The math is perfectly written. You confidently hit run before heading home.
And it starts cleanly.
Really?
You watch the logs, and batch 1 processes without a hitch.
Yeah, you're feeling good.
Batch 50 goes through perfectly.
Yeah.
You assume you were totally in the clear.
But then, right around batch 200, the entire pipeline crashes. Just bam, memory error.
Ouch.
Yeah, the system completely halts. And as the engineer, you come in the next morning and you're just sitting there scratching your head. You've got 64 gigs of RAM.
Right. Plenty of space.
And the architecture dictates that only one image is supposed to be in memory at a time. But in reality, well, it wasn't. A single, innocent-looking list in the code was appending every process slide and never releasing it.
Wow.
No crash warnings, no slowdowns, just this silent, invisible accumulation of data until the server choked.
It's the ultimate nightmare scenario. I mean, you miss a clinical deadline, you spend 3 days debugging, and the realization finally hits you. The model didn't have a bug.
Right.
The algorithm was totally fine. The bug was entirely in the data lifecycle.
Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Glad to be here for this one.
Today, our mission in this deep dive, which is APML 05, is walking you through the exact failure patterns that silently break ML systems, the core principles of memory management, and the precise tools you need to fix them.
Because honestly, before you can fix a memory leak in a massive neural network, you really have to understand the fundamental rules of how Python actually handles memory. You just cannot trust the system to do it for you.
Yeah, it's not magic.
Exactly. Specifically, we need to look closely at rule number 2. Every reference keeps memory alive.
Okay, let's unpack this. To understand how memory actually works in Python, we really have to look at the 2 layers running under the hood.
Right, there are 2 layers, and both matter immensely to how your code behaves in production. The first layer is the heap.
The heap.
Yeah. Think of the heap as this giant unstructured pool of RAM that CPython manages for you. Every single object you create a standard list, a massive NumPy array, a PyTorch tensor, a pandas data frame. It all lives somewhere on the heap.
Makes sense.
Python allocates space for it, and when you are done, Python is supposed to reclaim that space.
But supposed to is doing a lot of heavy lifting there. I mean, how does Python actually know when you are done?
Well, that brings us to layer 2, which is the reference system. Python tracks every single object on the heap using something called reference counting.
Okay, so it's literally counting.
Literally. Under the hood, in the actual C implementation of Python, every object has an internal counter. That counter constantly asks one question: how many variables or data structures are currently pointing to me in the active program?
So if I write a little script and use the sys.getRefCount function, I can actually see this integer changing in real time.
You absolutely can.
Let me give you an analogy to help visualize this mechanism. Think of reference counting like people holding a heavy door open.
I like that.
As long as at least one person, or in this case, a variable, has their hand on the door, Python absolutely will not let that door close. It won't free the memory.
Right, it's forced open.
Exactly.
Right.
Even if that door represents a massive 2 gigabyte tensor array, if the reference count is greater than 0, it stays.
And if we connect this back to our healthcare pipeline story, it explains exactly why that server died. The engineer assumed that because batch 50 was done processing through the model, its memory was automatically cleared.
Because it moved on to the next batch.
Right. But a background tracking list was still holding the door open. That list was pointing to the batch data. Python saw the reference count for that tensor was greater than 0, so the data never left the heap.
It's just silent accumulation. You think the memory is gone, but it's quietly piling up in the background.
Precisely. If anything, anywhere in your code points to an object, it stays alive.
But hold on. If reference counting is really that simple, just keeping a literal tally of who is pointing to what, why does it fail so spectacularly in modern object-oriented machine learning code? Because, I mean, I see memory leaks in PyTorch all the time, and I'm definitely not intentionally keeping old batches around.
It fails because of a structural vulnerability in how we write code. It's called circular references.
Circular references.
Yeah. A circular reference happens when two objects point to each other, creating a closed loop. Imagine a classic ML training setup. You have a trainer class, and that trainer initializes and holds a model.
Right.
But the model also needs to log metrics or trigger callbacks, so it holds a reference back to the trainer.
Oh, they're looking at each other.
Right. Now, what happens when your training job finishes? You delete the trainer variable. You delete the model variable. From your perspective as the programmer, those objects are gone.
Completely wiped.
You would think so. But on the heap, the trainer object is still pointing at the model object, and the model is still pointing at the trainer. Their internal reference counts drop, but they never reach 0.
Wait, really?
Really, they're isolated, completely unreachable by the rest of your program, but Python keeps them alive forever because they're holding each other's doors open.
But wait, Python has a garbage collector. I hear about the GC all the time. Isn't it supposed to be the ultimate backup system that sweeps up exactly this kind of mess? Why doesn't the janitor just come in and break up that little unkillable loop?
This raises a really important question, and it's a trap a lot of engineers fall into when they transition from standard web development to machine learning.
Okay.
Yes, Python has a generational garbage collector, specifically designed to find and destroy these circular references. It operates in 3 generations. Generation 0 is for newly created objects.
Right.
If they survive a GC sweep, they get promoted to Generation 1 and eventually to Generation 2, which is for long-lived objects.
Okay, so there is a mechanism. It does clean up.
It does clean up eventually,
Yeah.
and that eventually is the most critical reality check for an ML engineer.
What do you mean?
Well, the GC periodically pauses your program to scan the heap for these unkillable loops. But the GC is computationally expensive, so it doesn't run constantly. In a tight machine learning training loop, you are allocating heavy tensors, gigabytes of data, so incredibly fast.
Oh, I see where this is going.
You will hit an out-of-memory error, an own crash, long before the garbage collector ever reaches its internal threshold to wake up and run a scan.
You literally cannot outwait a memory leak in ML. The system runs out of physical RAM and crashes before the janitor even clocks in for their shift.
Exactly. The scale of the data breaks the safety net, which is why proactive memory design isn't just a nice-to-have, it is a mandatory systems design skill. We cannot rely on the GC. We have to recognize the architectural patterns that cause these leaks and prevent them entirely.
Here's where it gets really interesting. So we've established that manually appending data to tracking lists is a rookie error because you are explicitly holding the data. But what happens when the framework itself hoards data invisibly without you ever explicitly asking it to?
Yes.
PyTorch is notoriously guilty of this, specifically when tracking the training loss.
Oh, the GPU ghost. This is probably the most catastrophic leak in deep learning. You have a training loop running over hundreds of batches. Naturally, you want to track your total loss to calculate the average at the end of the epoch.
Sure.
So you write a simple line. Total loss plus equals loss. It makes complete logical sense, right?
Right. You're just keeping a running math tally. 5 plus 5 equals 10. It's just a number.
But here's the mechanism you have to understand. In PyTorch, that loss variable is not a simple float. It is a tensor. And attached to that tensor is the entire computational graph.
Wait, why does a simple math tally need a computation graph in the first place? I just want the numeric loss value to print to my console.
Because PyTorch doesn't know you just want the number for logging. PyTorch's autograde engine is designed for backpropagation, calculating gradients.
Okay.
To do that, it has to remember every single mathematical operation, every weight, and every activation that happened during the forward pass of that specific batch.
Oh, wow. All of that is attached.
All of that history is anchored to the final loss tensor. When you write total loss plus equals loss, you're accidentally telling AutoGrad to link independent batch calculations together. Batch 1, batch 2, batch 100. You are literally chaining 100 massive computation graphs together in your GPU's memory.
To use an analogy here, it's like trying to calculate your grocery bill, but instead of just writing down $5 in your notebook, you staple the entire receipt, the store's inventory log, and the cashier's timesheet to your notebook for every single item you buy.
That's exactly it.
Eventually, your shopping cart physically collapses under the weight of the paper. You don't need all that history just to know the total.
That is a perfect way to visualize it. You are hoarding history. And the fix is literally one method call. Instead of total loss plus equals loss, you write total loss plus equals loss.item.
What does dot item actually do under the hood?
It acts as a severing tool. Adding .item tells PyTorch to reach into that complex tensor, extract just the raw Python float value, and leave the computation graph behind.
Just grabs the number.
Yep. Because that raw float is no longer pointing to the graph's reference count drops to 0, and hundreds of megabytes of GPU memory are instantly released. It is a fundamental rule. Computation graphs are hidden memory.
Just typing dot item saves your entire pipeline. That's wild. But keeping with the theme of PyTorch, invisibly building things we don't need, what about when we aren't even training? What happens during model evaluation?
That is another massive pitfall. When you are running inference, just evaluating your validation set or making predictions, you are not updating weights. You do not need to calculate gradients.
Right, the training is done.
But again, PyTorch doesn't automatically know your intent. By default, it builds that massive computation graph on every forward pass anyway, allocating memory for a backward pass that is never going to happen.
So it's reserving all this memory for a job it's never going to do.
Exactly. If you forget to wrap your evaluation loop with torch.no grad block, you are literally doubling your GPU memory footprint for absolutely no reason.
Doubling it.
Yeah. You're storing intermediate activations that serve zero purpose. Your code runs significantly slower, and it crashes twice as fast.
Never evaluate without explicitly turning off the gradient engine.
Got it. Now let's look at how we actually get data into the model in the first place. I know I have done this myself when I first started. You write a beautiful, clean list comprehension in Python to load your data set. One line of code that reads every single image path and loads the array into a list before you even start processing.
It looks elegant, but it is structurally doomed. Totally doomed. If your data set is 500 gigabytes and your system RAM is 32 gigabytes, that elegant list comprehension will crash your machine before the very first image is even fed into the model. You are demanding the entire data set exist in memory simultaneously.
So we have to fundamentally shift our architecture, moving from loading everything to loading one thing at a time, which naturally brings us to what I consider the highest ROI tool in all of Python.
Generators.
Yes. Generators completely change how Python handles state. By changing a single keyword in your function from return to yield, you transform a memory crashing list into a stable, flowing stream.
So instead of trying to build a bigger warehouse to store all the data at once, you're just putting a conveyor belt right through the middle of the factory. You process a part, it moves down the line, and you never hold the whole inventory.
That's exactly how the memory state works. When Python hits a yield statement, it pauses the function, saves its state, and hands exactly one batch to the next step.
Just one.
Right. If you compose your pipeline, say a load function, a preprocess function, and an augment function, and they all use yield, they operate like an interconnected assembly line.
Okay, so step by step.
Exactly. The loader pulls one batch from disk, the preprocessor normalizes it, the augmenter shifts the colors, the model trains on it. At any given millisecond, exactly one batch exists in your system's RAM.
And the moment that batch completes the forward pass, what happens?
The variables in the loop are reassigned to the next batch. The old batch loses its references, the count drops to 0, and the memory is instantly freed. Your memory usage chart becomes a flat, stable horizontal line, regardless of whether your dataset is 10 megabytes or 10 terabytes.
Streaming always beats accumulation. But what about when we need to be really explicit? Let's go back to that circular reference problem with the trainer and the model.
Okay, yeah.
I see people out there using the del keyword to force delete variables, or manually calling gc.collect at the end of every epoch. If we have those explicit overrides, why should we bother with something complex like the weak ref library?
Because forcing gc.collect is reactionary. It's slapping a bandage on a broken architecture. You are acknowledging that you built a memory leak, and you're just trying to sweep it up before it crashes the server. Weak ref is true proactive engineering.
So how does a weak reference fundamentally differ from a normal reference?
A weak reference using weakref.ref allows the model to look at the trainer and access its properties without actually incrementing the trainer's internal reference count.
Oh, interesting.
It essentially says to the Python memory manager, I know where this object is and I will use it if it's there, but do not keep it alive just for me.
Hold on. If weakref is so perfect and doesn't artificially inflate the reference count, why don't we just use weak references for everything in Python? What's the catch?
The catch is exactly that. It doesn't keep the object alive. If you use a weak reference and the rest of the program moves on, The garbage collector will destroy that object.
And then what?
If you try to access your weak reference 5 minutes later, it might return none. You get none-type errors crashing your program everywhere.
Ah, okay.
You only use weak refs specifically to break architectural cycles, like parent-child relationships, where the parent strongly holds the child, but the child only weakly observes the parent.
Right.
When the parent finishes its job, its count hits 0, and the whole structure cleanly dissolves. You prevent the cycle from forming in the first place.
That distinction makes a lot of sense. You're designing the relationships, not just fighting the garbage collector.
Yeah.
We also need to talk about context managers. You mentioned the with torch.no grad block earlier. We see with OpenFile all the time.
Yeah.
What is the actual memory advantage of the with block?
The beauty of a context manager is that it provides a guaranteed cleanup crew. When you open a file or allocate a specific GPU context, you are borrowing resources from the operating system.
Okay.
If your code throws a massive error and crashes halfway through processing, the normal flow of your script stops. If you rely on manually writing a close or delete command at the bottom of your script, it will never execute.
And the file stays locked, or the GPU memory stays reserved, even though the program crashed.
Exactly. But a with block has internal dunder enter and dunder exit methods. Even if a fatal exception is raised, Python guarantees that the dunder exit method will run. The memory is released, the files are closed, and the GPU context is safely cleared. It removes human error from resource management.
Which naturally brings us to profiling. It's the X-ray vision for engineers. Because honestly, you can't fix what you can't see.
You have to measure memory. You can never guess. We rely on 2 primary tools. For Python's heap memory, we use a built-in library called Tracemalloc.
Tracemalloc. Okay.
It is incredibly granular. It doesn't just tell you that your memory is high.
Yeah.
It tells you exactly which line of code allocated the memory that isn't being freed, down to the byte.
Wow, that's specific.
It really is. For the GPU side, we use torch.no memory summary, which provides a complete breakdown of what AutoGrad and your tensors are doing.
When I'm staring at these profiler charts, looking at the memory allocation over time, what visual shapes am I actually looking for?
You want to see a sawtooth pattern. The line representing memory goes up steeply as a batch is loaded into RAM and processed through the layers. Then it drops sharply back down when the batch is discarded and the references are cleared. Up, down, up, down.
Like a heartbeat.
Yes. That means your system is breathing. It's allocating and releasing cleanly.
And a leak.
A leak looks like a staircase that never descends. You see the sawtooth, but the baseline keeps creeping upward with every batch. That tells you that some fraction of the data, maybe a computation graph, maybe a straight tensor, is being left behind on the heap.
Knowing these tools is one thing, but proving you know them when it matters is what separates junior candidates from senior engineers. Imagine you're sitting across from a FANG hiring manager. They slide a piece of paper across the desk and give you a scenario.
Okay, lay it on me.
Your ML training job runs completely fine for the first 100 batches, but crashes on batch 101 with a memory error. What is the first thing out of your mouth?
The absolute worst thing you can say, and the trap answer they're waiting for is, I would just provision a cloud instance with more RAM.
Right. Just throw your company's money at the problem.
Exactly. It proves you don't understand the underlying mechanism. If you have a leak, a larger server will just crash a few hours later. The senior answer is systematic debugging. You tell the hiring manager you have 3 hypotheses. 1, it's batch accumulation in a tracking list. 2, it's the PyTorch AutoGrad chaining computation graphs. Or 3, it's a circular reference in the classes. Then you explain that you would wrap the training loop with Tracemalloc, take a snapshot at batch 10, another at batch 50, and diff them to pinpoint the exact line of code that is monotonically growing.
So what does this all mean? Let's do another scenario to find out. The hiring manager pivots to data preprocessing. They ask you to explain the difference between a view and a copy in NumPy and why it critically impacts memory.
This is a deep mechanism test. A view in NumPy simply shares the original memory buffer on the heap. It just changes the metadata, the strides that dictate how you look at the data.
Okay, so it's just a lens.
Exactly. If you have an 800 megabyte array and you do a simple reshape operation, NumPy creates a view, takes 0 extra memory.
But what if I do a math operation? What if I add 0 to the entire array? Mathematically, nothing changes.
Mathematically, no. But computationally, NumPy is forced to allocate a completely new block of memory to store the result of that arithmetic. It creates a copy. You instantly jump from 800 megabytes to 1.6 gigabytes of RAM.
Oh, wow. From just adding 0.
Right. If you are building a 5-stage data pipeline, and you don't know the exact rules of which operations create views and which allocate copies, you will accidentally duplicate your arrays at every step. You turn an 800 megabyte footprint into a multi-gigabyte nightmare, all before the model even sees the data.
One last scenario. The hiring manager looks at you and says, design a pipeline to train on 500 gigabytes of data. But you only have a machine with 32 gigabytes of RAM. Go.
You immediately start by stating that memory efficiency isn't a feature you optimize for later. It's the primary constraint of the architecture. You explain that you would use a generator-based loader with yield to stream the data off the disk.
The conveyor belt.
Yes, the conveyor belt. You would structure the pipeline composition so that only a single batch exists in the Python heap at any given moment. You'd implement bounded prefetching queues so the CPU doesn't load data faster than the GPU can consume it.
Makes total sense.
And you enforce strict GPU memory discipline by ensuring gradients are zeroed and tensors are deleted immediately after the optimizer steps.
It all comes down to explicit control. You don't let the framework make assumptions for you. I want to challenge you, the listener, to actually feel this today. Don't just take our word for it. There's a micro exercise in section 13 of today's source material. Open up your IDE. Go build the leak.
Do it intentionally.
Yeah. Write a simple for loop that appends massive NumPy arrays to a global list. Wrap it in Tracemalloc and watch your RAM climb into the gigabytes. Feel the system slow down, and then rewrite it. Change that global list into a yield generator and watch the memory flatline perfectly. The numbers on your own screen will lock this mental model in forever.
That really is the final takeaway here. In machine learning, where we are dealing with gigabyte-scale tensors running continuously for hours or days, automatic machinery is just not enough. The Python garbage collector will not save you. Production stability is almost never about the brilliance of your neural network architecture. It is entirely about the explicit memory discipline of the engineer building the underlying system.
We've spent this entire deep dive making sure the pipeline doesn't crash from memory bloat. We've locked down the references, we've streamed the batches with generators, and the system runs perfectly for a week without a single memory spike.
Yep.
But I want to leave you with something to chew on. What happens if your memory management is absolutely flawless, but your model is silently outputting the wrong math? No memory errors, no crashes. The RAM is perfect, the code executes quickly, but the logic inside the tensors is completely poisoned. How would you even begin to know?
That is exactly what we tackle in APML 06. Debugging ML systems thinking, like an engineer. We are moving from managing the memory lifecycle to diagnosing correctness when systems fail despite doing everything right.
It's going to be a fascinating jump. Thank you for joining us on behalf of the 60 Seconds Academy. Keep building, keep measuring, and we will see you in the next deep dive.